In the previous lesson, we solved the short dipole by exploiting one key fact: the source was bounded. Because the current existed only along a finite stretch of wire, we could pull the common amplitude factor 1 over r outside the integral and keep only the source-dependent phase inside. That approach gave us the clean sine theta pattern. But now imagine a current filament that stretches to infinity in both directions along the z-axis. The bounded source shortcut we relied on no longer applies directly, and we need a different evaluation strategy. Place the infinite line source along the z-axis, carrying a uniform current I0. The observer sits at a cylindrical distance ρ from the wire. The vector potential integral now runs from -infinity to +infinity. Each source element at height z prime contributes through the kernel e to the minus jkr divided by r, where r equals the square root of ρ squared plus z minus z prime squared. Writing this integral is straightforward. The real question is how to extract a useful closed-form answer from an integral whose limits stretch to infinity. Plot the phase function -k times r as a function of z prime. Near the observer's own height z, the phase changes slowly because r is near its minimum value ρ. But as z prime moves away from that point, r grows and the phase drops steeply. The integrand oscillates faster and faster. These rapid oscillations mean that positive and negative contributions cancel almost perfectly. Only the slow phase neighborhood around the nearest point adds coherently to the integral. The stationary phase recipe formalizes this observation. Set the derivative of the phase function with respect to z prime equal to 0. For our distance law, the derivative of -kr vanishes when z prime equals z, the observer's own height, that is, the nearest point on the wire. The second derivative there equals -k over ρ, which tells us how narrow the contributing zone is. A larger ρ means a wider neighborhood contributes, while a shorter wavelength tightens the zone. Applying the stationary phase approximation gives the vector potential proportional to e to the minus j k ρ over the square root of ρ. Compare this with the bounded dipole, where the answer was e to the minus j k r over r. The infinite line source produces a cylindrical wave. Energy spreads over expanding cylinders instead of expanding spheres, so the amplitude decays as 1 over root ρ rather than 1 over r. This slower decay reflects the fact that the line source maintains coherent radiation along its entire length. The physical picture is elegantly simple. Even though the wire extends to infinity, the radiation at any observation point comes predominantly from the nearest segment. Distant parts of the wire contribute rapidly oscillating phases that cancel through destructive interference. The effective radiating zone is centered on the nearest point and has a characteristic width proportional to the square root of the product of wavelength and distance. The infinite line source via stationary phase summarizes in 3 layers. First, the source is unbounded, so pulling 1 over r outside does not work. Second, the stationary phase method identifies the dominant contributing zone around the nearest source point. And third, the result is a cylindrical wave with 1 over root ρ decay, matching the cylindrical symmetry of the infinite geometry. This lesson and the previous one form a complementary pair. The far-field approach handles bounded sources by exploiting a shared observer distance. The stationary phase method handles extended sources by letting the phase landscape select the important zone. Together, they give us the complete evaluation toolkit for radiation from any current distribution.